Ladies and gentlemen, let's game into the video. Let us discuss DirectX 12, the low-level API. It's going to be an analysis of what we currently know. There's also an associated article for this, and it's going to be quite in-depth. There are quite a lot of things that we discussed in the article. I possibly won't be able to cover them all in this video simply because for the sake of brevity. So if you do want to check something out, then you can check out the article. It has got some images in there. It's also got some links to sources and other bits and bobs that you would expect. So now that's all out and over with, let's discuss DX12. So at GDC 2014, of course, DirectX was unveiled, the newest iteration. But before that even, we knew that there was going to be a low-level API release from Microsoft, and we didn't really know too much about it. What we do know is that if you've got a GCN-based GPU, so like a Radeon 7000 or above, or a Fermi-based graphics card, in other words, like a GTX 400 series or above, you're good. As for Intel owners, you're going to have a Haswell-based GPU, and we'll go into that in just a moment. So there are still quite a few features of DirectX 12 that Microsoft are keeping very close to its chest, even including which operating system it's going to require. People, including myself, are probing them, and I've asked them questions, but they basically just told me to refer to the blog, which is very different to AMD handled the Mantle issue. But you've got to remember that Mantle was a lot further in development compared to what DirectX 12 is now. So there's a few questions that a lot of people are asking. The first is, why is DirectX 12 so focused on low-level access? I mean, a lot of people expect, you know, new standards, for example, for the graphics core, for the graphics card. For example, we might see new lighting techniques, so we might see improvements here or there for various graphics related libraries. But right now, the main thing that Microsoft have announced is low-level access, low-level improvements. So we're going to be getting much better improvements for the low-level access to the for the graphics card. And why is that? Well, we have to do a little bit of backtracking to really understand this. So before Mantle was announced, which was of course the later half of last year, it's fair to say that a lot of people in the PC industry were getting fairly pissed at the state of APIs. By the way, APIs stand for Application Programming Interface. Quite simply put, there was just seemed to be like a lack of care or a lack of improvement in them. There were a few extra features added, and DX11 did improve multi-threading somewhat over DX10 and so on, but there wasn't huge improvements. And especially when you consider that PCs typically simply overpowered problems. By which I mean that if you were to look at the improvements on CPU and GPU, you would see them going up fairly straight line, and you'd just see, okay, well, it doesn't really matter if it's not super duper duper efficient, we could just go simply for a faster CPU. It was a fairly simple solution. Maybe not an elegant solution, but a solution. Consoles like the PS4 and Xbox One are fairly easy. If you were to buy a PS4 right now, just for example, it can easily be interchanged for an Xbox or whatever console, but let's just say you buy a PS4 and then your friend Bob buys one 2, 3, 4 years from now, it doesn't make a difference. He might get a faster hard drive or a bigger hard drive, he might get a smaller form factor, maybe his console will run a little bit quieter, whatever. The reality, however, is that his CPU clock speed is going to be the same, the amount of cores available in his system are going to be the same, the amount of T-flops of computing power that his GPU has is still going to be the same. In other words, the core specifications aren't going to be any different. This in turn means it's very easy to create low-level APIs, as well as high-level APIs. Typically consoles do have both. So if you don't require the specification or the performance of low-level, you can basically code in high-level. But if you do need that low-level performance, you can do that, and we'll discuss that more in just a moment. So it's basically written in a way to take full advantage of the specifications. So that means that low-level hardware, at least if you compare it to like a PC part, could basically be a lot more efficient than what it would be if it was on a PC. So that means, for example, if you were to take exactly the same graphics card from the PS4, you were to transplant it along with the CPU into a PC, you're going to get worse performance on the same game, at least theoretically. Now obviously how much worse performance really depends on the game and the game engine and the driver, but generally speaking. So PCs traditionally work using two different types of APIs. There's DirectX or Direct3D, or of course OpenGL. By the way, OpenGL stands for Open Graphics Library. Obviously DX is handled by Microsoft. OpenGL is handled by the Cronus Group. They're the developers. Now the benefit of OpenGL is that it can work on a variety of different platforms. So for example, there's Linux, which of course it supports, as well as Windows, and of course there's also WebGL and various other GL for like mobile devices and stuff. On the other hand, Direct3D is handled primarily for consoles. Obviously you've got the Xbox One, you've got Windows, and also some parts of the phone as well. Some phones, of course, Windows phones can do it as well. But these are typically higher level than consoles. In other words, what this means is that you've got a fairly thick abstraction layer. So the game basically will speak to DirectX and will pretty much tell DirectX what it needs. DirectX will then speak to the graphics driver, which will finally speak to the GPU, and then it will tell it, hey, I need you to draw this on screen, I need you to create this box, and this box needs to be yay big, and it needs this color, and it needs to be lit in this way. And these are all different instructions that are being sent to the graphics card. So the last time we really had a low-level API, other than Mantle of course, but apart from Mantle, would be from 3DFX, and that was the Glide API, and it was specifically written for the Voodoo graphics cards. And basically popular games of the time, for example the Quakes and the Tomb Raiders, would be released with a patch to enable Glide. So that's great and all, but unfortunately you can't continue on that path. What's basically happened is that there's a huge variety of different hardware possible varieties on PCs, right? So I could have 4 gigs of RAM, you could have 6. I could have a 6-core processor, you could have 8. You could have an AMD graphics card, I could have an Nvidia graphics card, and even assume I do have an Nvidia graphics card. Which graphics card? Okay, I go with the GTX, let's say 670. Okay, which one? What? I hear you scream. Well, GTX 670, which clock speeds? More to the point, are you going with the 2GB or the 4GB graphics cards? There's a lot of different moving parts to this. It's not really simple. And so what generally happens previously is that we've got a higher level API. Basically the API takes the commands, it will make them in kind of like a common different structure that the driver itself will then interpret those commands and then issue them to the graphics card. And there can be some level of optimization there, because pretty much what happens is developers will release their game, and obviously there might be patches which slightly improve the game performance, but also AMD and Nvidia will release new drivers which will improve performance. And this is very important for like AAA titles. But unfortunately this does have some drawbacks. CPUs of today, as we've discussed previously, aren't really making the same performance gains they were, say, several years ago. This is true on both consoles and PC. Basically, what we're talking about here is the per-core/thread. Now, IPC, which by the way stands for instruction per clock, improvements are vastly slower than what they were. Back in like 2000, early 2000s, even like the late 90s, early 2000s, it was incredible. There was like always just every single CPU generation was pretty impressive, and basically it was great, but unfortunately you can't keep doing that. Simply put, increasing clock speeds isn't something you can just do forever and a day. What happens is that Intel found this out really in like a really harsh way from the Pentium 4 architecture, which was the original one, was known as NetBurst, by the way. And they boasted constantly that they could actually get it up to 10 gigahertz. They could run the CPU at 10 gigahertz. In reality, that's not what happened. They suffered from a major heat and power issues, power leakage, other issues as well. Suffice to say, they hit about 40% of that number. Now, if you were around in like the mid-2000s and you were one of those people who were like doing world record attempts at Pentium 4 overclocking, sure, people were doing like 5 gigahertz, 6 gigahertz or whatever, but they were using very extravagant cooling methods to do so. They were not using just the simple air cooler that like 99% of people were using. And so basically speaking, you can't just have this situation where you're just forever and ever and ever increasing clock speeds, and so you have to start going for better what should I say, improvements on like threads, so more multi-threaded. So IPC hasn't really improved that much. If you look at Intel, for example, with the Sandy Bridge to Haswell, it's only about 20%, despite the fact that it's been like 3-4 years now since the architecture has emerged. And okay, they're not. It's not really like a tick-tock kind of scenario, but even so, you know, Haswell has some extra instructions like AVX2, which obviously the previous one didn't. It only had like AVX, but even so, in most situations, only about 20% faster, which isn't really that huge. If you compare that, however, with GPUs, graphics processor units, it's not even in the same league, right? GPUs are just going off through the stratosphere. It's just incredible. Now we've got GPUs which are like, you know, 2 T-flops is nothing for a GPU now. 2 T-flops is like mid-range at best. Now we're hitting GPUs which are going to be like 4, 5, 6, 7 T-flops, and it's only going to increase as like the newer GPUs are released. To put that into perspective, the PS4's CPU runs at roughly 100 G-flops. Now, I say roughly because we're not exactly sure of the clock speed of the PS4's CPU. It's between 102 and the low 110, so maybe 110, 112, something around that line, depending on the clock speed. Regardless, it doesn't matter what it is, because the PS4's GPU, on the other hand, offers a rather ludicrous 1.84 T-flops. And considering there's 1,000 G-flops in per teraflop, you can kind of see how that it's not even comparable. So when you consider the vast amount of the work that a CPU does is actually preparing jobs for the GPU. We'll get more into how this works in just a moment, by the way. But it basically does this primarily on a single thread on DirectX and most other high-level APIs. So what happens is that single thread basically gets overwhelmed, and then you get into situations where it doesn't matter about the other threads. For example, let's say you've got 4 cores on your CPU. Core 234 could be basically doing 25% of the work, or 25%, so they're loaded like 25%. And in other words, they've got 75% free processing power, but Core 1 is just completely and utterly overwhelmed because it's handling everything. It's handling the graphics driver, it's handling issuing out all the commands. It just simply can't cope. And the PS4's API is not only lighter, but it's also a lot easier to basically issue these threads, or should I say the rendering over multiple processors, and this means that in turn the GPU isn't really waiting. And this is another issue that we've discussed heavily before in regards to draw calls. Naughty Dog, by the way, have already done a technology breakdown on how the multi-thread works on their own title, so you can check that out. So we've got Mantle out right this second, right? So Mantle's available now. The problem with Mantle is, well, it's still A, in development, and B, there's still not all the games that support it. In fact, there's not that many compared to, say, DirectX. DirectX, on the other hand, well, it's not out yet. It's that simple. So we don't really know the situation in terms of how many games are actually going to support DirectX by the time, support Mantle by the time that DX actually finally emerges. So now we're on the pretty much the same page as to why DirectX needs to be a low-level API. So the question is, how is it going to achieve that? Because how and why are two different things, as you can imagine. There have been comments from others regarding AMD's Mantle versus DirectX in terms of similarity, and some people are saying that it's more than a little bit similar, and there are some accusations regarding the fact that Microsoft have ripped it off. Now, I don't want to get drawn into that really, but I have done a brief interview/discussion with AMD. I've linked it in this particular article. This will be the second page of the article. And during the interview, basically they said that DirectX is their own creation, but they weren't hesitant whatsoever to point out that they certainly inspired it heavily with Mantle. So I'm going to let you guys kind of draw your own conclusions for that one. So anyway, how is it going to achieve this? Well, there's several different ways it's going to do this. Basically, there are going to be multiple changes. Now, I certainly haven't listed all of them yet, but there's going to be differences in terms of command list and command buffers. There's going to be improvements, or should I say, the addition of pipeline state objects, descript heaps and tables, as well as conservative rasterization are just some of the methods they're going to be using. So what exactly is this? Well, let's discuss command list and command buffers. So it's little doubt that the largest source of the overhead woes for the command buffers and lists, as the CPU assembles the commands for the GPU to process. So basically, DirectX 12 is going to overhaul the methods completely and utterly from previously, from DirectX 3, from DirectX 11, shall I say, because what it's going to be doing, rather than DX11 handling all the process pretty much autonomously, instead it's basically going to fall to the game's developers to create their own command lists. So in effect, the developer can take more readily take advantage of multi-core CPUs, and they can spread the workload over the CPUs. Unfortunately, if you were hoping to get a look at the code or to really kind of figure out how this is going to work, you're not going to be really well served, because unfortunately right now Microsoft aren't really pushing that much detail to us. But what we can do is to provide a brief overview on how this works. So GPUs are what is known as in-order processors. This basically means that they take data as it comes, and they have to process that in that way. So basically speaking, CPUs are out of order. So a GPU is basically a shared resource. In other words, multiple applications can use this hardware. A simple example of this is some of your GPU memory is actually taken up by Windows, so even when you go and play your game, let's say for example you've got 2 GB of memory on a graphics card, a certain amount of that, let's say 300 megabytes or whatever, might be taken up with, say, Windows. And sometimes it might purge it, but generally speaking, when you're alt and tabbing and stuff. So anyway, basically what happens is through the command buffer, you set the GPU to fetch the data, whatever piece of data that is, and then you process that data. And Microsoft are actually reporting that they're going to be introducing bundles, which are very similar to what you'd expect. They're basically bundles of command buffers, but they're actually reusable. So rather than that single command, right, which you're actually filling inside the command buffer, rather than that single command, instead these are like bunches of them, which in theory saves CPU time, because they're basically executing this whole bundle rather than, okay, you have to take this, you have to take this. It's kind of like me giving you a large box filled with stuff rather than giving you separate boxes, and then you have to take each of those boxes from my hand. I can just simply give you a larger box. Very vastly simplifying it, but still. Now that's not to say that each and every time that bundle has to be exactly the same. I used an example in my article of like, let's assume, just for the sake of simplicity, that the commands inside this bundle like 1 + 1, 2 + 2, 3 + 3. Well, the next time that bundle might have to run, it might have to be like 1 + 1, 2 + 2, and then 3 - 3. So in other words, there can be some differences. Microsoft are keen to point out that one of the reasons that one of the examples they're using for this, by the way, is a character. This is a character drawn on screen. That would be, a dude or whatever. And once he could be rendered with one set of textures, another time he could be rendered with a completely different set of textures. So let's now discuss PSO, also known as Pipeline State Objects. The previous iterations of D3D allowed the architecture switch between different pipeline states. Unfortunately, most modern GPUs don't really operate this way, and so the driver can't really resolve what's actually happening until it's basically draw time. So basically what happens is this vastly increased the CPU overhead, because what it's basically doing is that it doesn't really have to worry about the hardware state not being set until, well, draw time, so it doesn't really have to wait on it per frame. So once again, you've got to remember that this is not just like 1 or 2 draw calls per frame of animation, considering most games now are hitting 30 frames per second plus, and let's face it, who really wants to game at 30 frames a second if they can go to 60? So what really happens here is, of course, most games now operating thousands of draw calls per second. And so for every object in the game world, let's say you've got different textures and effects applied. So basically draw calls are basically the process of actually asking for an object to be, well, drawn on screen. In other words, you want that box drawn, my friend. Well, okay, that's going to cost you a draw call. Well, you want that box lit? Well, okay, guess what? And so forth, and so forth, and so forth, and so forth. There's a fairly interesting one that Microsoft are also pointing out, and that would be the script heaps and tables. Now, from Microsoft's own notes, it seems that they're basically trying to introduce bindless resources into DX12, but they're not calling them that. Effectively, it seems to be, and that's very similar to what Nvidia actually pushed into their own hardware back in like 2012, but it wasn't really that readily supported. So it basically will expand the resources available to a program, shader program, and as well as even outright dynamic indexing of resources. So once again, this is going to be improvement in multiple different ways, and the final one is conservative rasterization. Now, the basic premise here is to improve object culling and collision/hit detection. Now, Nvidia have already created a technical description of this on the GPU gems, and it kind of gives a brief summary of it. It says this solution to these problems can be seen as a modification of the polygon before the rasterization process. Overestimation of conservative rasterization can be seen in the image process called dilation of the polygon, the pixel core. Similarly, underestimation of conservative rasterization is erosion of the polygon by the pixel core, by the pixel cell. Therefore, we transform the rectangular polygon overlap test conservative rasterization into the point of the region test. Now, if you're not exactly sure what any of that means, effectively speaking, they are working on ways to reduce the overheads of objects and also to improve the collision and hit detection, which has been a really big problem in games for quite a while. And there are many ways to handle this right now, which are being used. I mean, for example, one of the potential problems that has, one of the potential methods for this rather, is to, for example, increase rendering resolution. But it doesn't really guarantee the correct results, and even so, you're increasing the resolution, which means you're basically using more power. So obviously in that respect that's pretty sweet, assuming of course it all works. There's also been a few others. There's also compressed resources, which has been specifically mentioned, JPEG, as well as ASTCLDR, Once again, all this is written down in the article if you want to Google it. But that's already available for OpenGL, so that's not really news. But what is surprising is JPEG compression. But considering JPEG compression isn't really a fixed ratio, if you're even slightly familiar with web graphics or Photoshop, you're going to know that already. So with GPUs already liking predictable data, and architecture's currently not really supporting this, it's a bit of a strange decision, unless of course it's possible that Microsoft might know about something that's going to be happening in the future, and there's pretty likely they are actually going to know something that we don't in their market. So finally, let's discuss how all of this is going to work, because we've discussed already that, okay, abstraction is what a DX11 allows multiple pieces of hardware to run, but it takes its pound of flesh in terms of performance. So abstraction is basically a way of games running on different hardware. Now remember, DX12 is going to be able to be backwardly compatible with DX11, right? But, so in other words, just to reiterate, if you've got a DX12 card and you've got DX12 software, but your game isn't DX12, or in other words, the application is say DX10 or DX11, it's still going to be able to run. Fine, great. But Microsoft aren't really willing at the moment to give details on how the low-level access for the graphics cards work, which is a bit of a sad face. I have spoken to them, and they've not really given me any straight answers, if I'm totally honest, and so we have to be a bit sleuthy here. Actually, the key comes from not Nvidia's, but the combination of Nvidia supported and AMD supported cards, and you could kind of figure it out, because basically AMD's previous architecture before GCN, which as I mentioned is 7000 plus, is actually based on VLIW. Now I've discussed this already on the channel, so you can search for that if you want, or even on RGT website you can just type in VLIW and it'll pop right up. But now the switch to a SIMD GCN type of architecture, it's fair to say that that's a lot more Nvidia-like, right? Just in basically how they've structured their rendering pipeline, and now this means there's a lot less which separates all the free hardware vendors. That's not to say that they're exactly the same, that's not to say that all of their rendering pipelines are exactly the same. They've still got different ROPs, they've still got different amounts of TMUs, they still handle some of the stuff a little bit differently, as well as their drivers, but there is still a lot more similarity now in terms of the architecture. So there's obviously still going to have to be some level of the abstraction between the three vendors. Now, one theory is that developers could actually write their own hardware paths based on the GPU. That's just my own theory, but it would also require quite a lot of work on the hardware, well, on the software developer side, and was the game designer, so I don't really necessarily know if they're going to do that. In one respect, it could be kind of bad if that's true, because let's say it's a sponsored by AMD game or sponsored by a Nvidia game. In theory, we could be seeing some performance issues there. I don't necessarily know if that's the case, however, that's just like kind of a doomsday scenario with this, but I don't necessarily know if there's enough supporting evidence. That is, however, to say that there is definitely a much higher level of parity than what there was previously. It's also worth noting that, as I've mentioned earlier, Mantle is already out. Now, one curiosity is, well, let's assume a game supports DX12 and Mantle. Because there's got to still be that level of abstraction there, is it possible that DX12 is going to be outperformed by Mantle and AMD's own hardware? Well, I don't know, to be honest. I wouldn't be surprised, but it's hard to say. It's also worth noting that Microsoft themselves do have several motivations for all of this. It was fairly obvious to anyone that OpenGL would eventually push low-level optimizations. It was just inevitable. For a start, they're an open company, like a consortium of different standards and a lot of different contributions to it, particularly from Linux. And as I've mentioned before, they work with different pieces of software, with different operating systems and so on. And let's face it, if it was to happen, if low-level access from OpenGL, it would quickly start to push D3D, assuming D3D was still DX11 and they hadn't gone their own low-level route, it would start to push them into the cold pretty quickly. And that would be really bad for Microsoft, because then there would be a lot less reason for people to really focus on Windows gaming, because let's face it, D3D and the compatibility that it offers is the main reason that a lot of PC gamers stick with, well, Windows. If, on the other hand, there was better performance on Linux, and not really any major side effects to jumping ship, well, a lot of people would, particularly when you consider that A, Valve now are supporting Linux, and B, it's free. So that's definitely something for you to think about. And there's another argument as well that comes from Xbox One and the PC. Obviously, from the perspective of it's going to be a lot easier for developers to actually push a game onto the Xbox One and port it, which is definitely going to be an advantage, considering that people are already bitching and whining, not in a harsh way, but let's just be honest, a lot of people are complaining regarding Xbox One development and it not being really simple. In this regard, Microsoft are actually doing themselves a huge favour. So, it's going to be kind of interesting, because the PC market is definitely going to change a lot with the introduction of DX12, but no one exactly knows how much, and just if it's going to be, the Mantle is really going to be a great piece of competition. Obviously we've got OpenGL as well. Anyway, there is a lot of other pieces of we have to do a technical analysis for, but it's already 30 odd minutes for this video, and I think it's a good place to call it. There's going to be another article coming up the next day or two where we're going to be really discussing how this is going to impact console implementation, mobile development, and other bits and bobs as well, and going into some more technical details of all this, so hopefully you'll stick with me on that. Anyway, I'll see you soon, take care, bye for now.